Okay, this is part 2 of the final review. Which of the following are probability distributions? Remember, there's a couple of things associated with probability distributions. One, probabilities have to be between 0 and 1, and the probabilities have to add up to 1. Now, you don't really care about the x values. You don't care about, that's just data. So, x is just data. So, it doesn't matter here. When we're talking probability distributions, we're looking at the probabilities here. So, 1, the probabilities are between 0 and 1. If you add these together, you get 1. So, yes, this one's a probability distribution. For the second one, here we have a negative probability, so it is not. For the third one, here are percentages. Well, it's really no different than decimals. But if you look, all of them are non-negative, between 0 and 1. If you add these together, you get 1. So C is a probability distribution. And for D, well, here's a probability which is larger than 1. Can't have it. So no. All right, moving on. The average full-time faculty member in a post-secondary degree-granting institution works an average of 54 hours per week with a standard deviation of 2.1. So we know the mean is 54. The standard deviation is 2.1. We're assuming a bell-shaped distribution. This, to me, is aiming straight for the empirical table. We want what percentage of faculty members work more than 58.2 hours per week. All right, so let's just draw a picture here. Here's the mean, okay, and here's 58.2, okay, 58.2. Now, I might have the answer incorrect on this one now that I have to go back and look at the question here. But anyway, so we want what percentage of faculty members work more than 58.2 hours. Right here, that's what we're looking for. What percentage is there? Well, if you look at this bell-shaped distribution, it's suggesting the empirical table, okay? Or you can work with the normal table. All right, well, let's see what we get here. All right, well, anyway, if you look at the difference between 54 and 58.2, that is 4.2 units, right? If you divide that by 2.1, we get 2. In other words, there are 2 standard deviations between 54 and 58.2. Likewise, there'd be 2 standard deviations in this direction. The empirical table tells us that the percentage of data within 2 standard deviations of the mean is 95%. But this is not what we're looking for. We're looking for what's greater than that. Well, if we're looking for what's up in this direction here, we know on the outside of this circle is 5% of the data. So half of 5% is 2.5%. And so we expect 2.5% of the faculty members to work more than, can't see it now, 58.2 hours. You can also use the normal table and convert this to a standard normal distribution, and you'd probably get a very close approximation. Okay? Moving on. All right, compare Chebyshev theorem and empirical rule. The only difference between Chebyshev's and empirical rule, both of them are about percentages of data that is within some particular number of standard deviations of the mean. Chebyshev's applies to all problems. The empirical rule, you require a bell-shaped distribution. So Chebyshev's works for any case, but it's the worst approximation. Empirical rule, you need a bell-shaped distribution. Both of them are about the percentage of data within so many standard deviations of the mean. Here we go. The average cost for a certain type of grass seed is $4 per box. The standard deviation is 10 cents. what is the cost range for which at least 88.9% of the grass seed will sell? If you think about Chevyshev's theorem, it says that at least 1 minus 1 over k squared is the percent of data that is within so many standard deviations of the mean. Okay? Well, this percentage is given to be 0.889. If you solve for k, that's what I'm going to let you do. You solve this for k, and you're going to find out that k is approximately equal to 3 standard deviations. So, sigma times k is 3 times 0.10, which is 0.3. So if we add 30 cents to 4, and we subtract 30 cents from 4, we're going to have an interval where at least 88.9% of the data is going to be within those two numbers. Moving on, I think this is the, oh no, not the last problem. Have a probability problem. This problem is very often on the final exam. Something like this at least. Person selected at random, you read the problem here. We want the probability the person is married. He or she is the person's married and is a stock clerk. You want the probability that they're married and they're a stock clerk. Okay? So, how many people are married that are stock clerks? 12. How many people are there? Well, we have to add this up now, because this is our table. We don't have the actual number anywhere given. So 8 and 12 is 20, 23, 23, 25, 30, 45. So I get 45, so 12 over 45 for A. For B, the probability the person is not married. The number of not married people are here. That is 22. There are 45 people. Moving on. Okay, I'm probably going to need more room here for this one. Okay. Let's see what I got here. We're going to try to make some room here. Let me pause this for a second. Okay, I had to add myself some space here. So, again, this is not edited. Alright. The average age for a registered vehicle is 72 months or 6 years. We have a standard deviation of 12 months. So we know the mean is equal to 72. The standard deviation is 12. We choose a vehicle and we want the probability that that vehicle is more than 80 months old. And we want to round our answer to the nearest 4 decimal places. Okay? Now, we're assuming a normal distribution here. So the first step is to convert this to standard normal, right? So Z greater than 80 minus the mean divided by the standard deviation. So this is the probability that Z is greater than 0.67. If you look this up in the table and you subtract the percentage from 100%, because again this is the opposite direction, you should get an answer of, I'm looking at our work here, 0.25149. I can't read my own handwriting. Okay, but that's a very basic problem. You're just finding probability associated with the normal distribution. Standardize it, work with the table. For B, I'm going to erase this so I can see B right here in front of us. For B, the key word here is we want the probability that from a random sample, the mean is going to be more than 80. So for B, we're looking for the probability that X bar is greater than 80. When we're looking for probabilities associated with the mean of a sample, we think central limit theorem. And that means we have to work with the conversion formula, x bar, x minus the mean, divided by sigma over the square root of n. So in this problem here, the probability that x bar is greater than 80, the mean is 72, the standard deviation is 12, and the sample size is 32. When you do the math, this is the probability that x bar is greater than 3.771. Okay, and that's right, so I'll check that. So we want x bar to be greater than 3.771. Well, if you look at the table, I don't think the table goes out that far. Let me look in the table. Yeah, if you look at the table, it don't go out that far, which essentially means that the percentage of data above this is 0. Moving on. Okay, here's the last problem. Let me adjust this right quick here. Use a standard normal distribution to approximate 77% of the U.S. homes Oh wait, let's see. I think I have a. I'm gonna skip this one for now. I'm gonna have to look at this one because I think I wanted this to be changed to at least. Okay, so that I have to look into that. So I'm gonna skip this one for now. Okay, but I think I have something in my notes. I wanted that changed. I'm gonna have to look. All right. Anyway, the last one then I'm gonna work with. In the recent study of 200 people in Miami, it found 54 people were obese. Find a 95% confidence interval for the true proportion of individuals living in Miami who are considered obese. So we're told n is equal to 200. We are looking at proportions. So p hat is going to be 54 over 200, the proportion, which comes out to be 0.27 approximately. So q hat is going to be 1 minus 0.27, which is 0.73. Now, since we're looking at a confidence interval for proportion, we're going to be working with the formula p hat plus or minus z times the square root of p hat q hat over n. We're going to have to look up z for a 95% confidence interval. And z for a 95% confidence interval turns out to be 1.96. Alright, so now all we have to do is calculate z times the square root of p hat q hat over n. When you take your math and work with all these numbers here, you should get 0.0615. This is then added to p hat and subtracted from p hat to give you the interval 0.2085, 0.3315. Okay, so that's it. I'm going to look at this one here. I don't know what I'm going to do with this just yet, but I had wanted this to be at least 65. So let me just do that. I'm going to just change this to at least 65, greater than 65, because I wanted to illustrate, again, this is a binomial, and they want to use the standard normal to approximate it. So let's just I'll just set it up for you while I have the video going here. Alright, so looking at this problem here, let's just erase it here so I can look at it. Again, I'm not going to do 65 or less, I'm going to do greater than 65. So we want the probability that, from a random sample, the probability that someone does not have an answering device. Okay? They do not have an answering device. Okay, so I rewrote this so you can see what I'm talking about. At least 65 do not have an answering device. Okay? So, the probability that x is greater than 65 is going to be the probability that x is greater than 65.5. And the reason being, again, this is going to a binomial type distribution. We're going to use the standard normal to approximate. So we have to get rid of the 65 because at least 65, I need included, at least 65. So this is going to be 64.5. Okay, trying to rush here. 64.5. All right? All right, that's what we want. At least 65, so we have to include 65, so we're going to go down below 65. We want to be over here. We want to include it, so 64.5. Again, this is not edited, so it is what it is. If you don't want to use it, you don't have to use it. All right, so anyway, now I got to look at converting this to standard normal. Since we're talking about they do not have an answering device, okay, the population of 77% have an answering device. So, in this problem, n is equal to 290. Probability of success is going to be 23%. Why? Because we're looking at they do not have an answering device. It's telling us 77% do. So really success here is that they do not. So Q is going to be 77%. You got to convert this to standard normal, meaning n times p is equal to the mean. Square root of npq is equal to the standard deviation. And then you're going to convert this to a z-score. I'm going to let you do that because we're really running out of time. Minus the mean over sigma. And look this up, and then you have it. Okay, I'm sorry that this last one is a mess here, but again, this is not edited. Thank you.